So we had just done with lattice energy, and we had Alicia, was I here? Can you hear me?
Yes, sir.
So we did lattice energy, which was what basically. Actually, I can't. I said that was basically. So we did atomization as well. Atomization was that you just make one mole of gaseous atoms. That's it, and for that, from its elements, you take an element and you turn it into gaseous atoms. Sodium, gaseous atoms. That's it. Similarly, iodine, solid, turn it into gaseous atoms. That's it. So this was atomization, and you had and we did lattice energy, which was we did that in detail. That what is lattice energy? That you make one mole of lattice from its gaseous ions, which was basically bond formation. That gaseous ions, positive and negative ions, they all join up to form this ionic lattice, like a crystal of a salt. And that depended on two factors, which was how strongly do the ions attract each other, and that depends on the size of the ion, and it depends on the charges on the ion. The greater the charge, the stronger the attraction, and the smaller the size of the ion, the closer they are to each other, which leads to stronger attraction. So there was a concept of charge density that we did. If you have a stronger charge density, the lattice is going to be stronger. And so we did all of that. We were doing electron affinity, which was let's say electron. Hold on a second. So electron affinity. This was exactly the opposite of ionization energy. It's the energy that is, I'll write down the definition for this, that it's the energy that is released or absorbed. It could be endo, it could be exo as well. So it's the energy released or absorbed when one mole of gaseous atoms so one mole of gaseous atoms or ions gain one mole of electrons. And they end up forming one mole of gaseous minus one ions. Now, when it comes to electron affinity, which is exactly the opposite of ionization energy, that an atom or an ion starts to gain electrons. I told you that you don't write that it's the first. I mean, you don't write the terms first or second. All you write is electron affinity of Cl. That's it. I mean, this one is who's gaining the electrons. It's Cl that's gaining the electrons. So this one is the electron affinity of Cl. That's it. And similarly, this one is electron affinity of I mean, this one is electron affinity of. Sorry, that was the ionization energy of Cl, where the electron was getting removed. Because that's the first. This one is the electron affinity of Cl atom. Similarly, an ion could gain electrons. For example, oxygen minus one can gain electrons. So if I write down electron affinities of oxygen, so that's an oxygen atom gaining an electron. And when it gains an electron, it would form oxygen minus one gaseous. And it usually gains two electrons. So it's going to be oxygen minus one gaseous that gains another electron, one mole of electrons, and they end up forming oxygen minus two ion in gaseous state. Just hold on 1 second. So the first one is the electron affinity of oxygen atom. The second one is referred to as the electron affinity of oxygen minus one ion. Okay, so they don't use the word first or second. They just call it who's gaining the electron, and that's it. That's the electron affinity of that thing. Okay, is this clear? Electron affinity. What is electron affinity?
Yes.
ठीक है बाकियों clear? Asim, is this clear? Hani, is this
Yes.
clear? I said, anyways, can anyone tell me, is this going to be exo or endo? Like ionization energy is when you're trying to remove an electron, right, from an atom. That is endo. It requires energy. You have to sort of pull the electron away from the atom, right? When you're giving an electron to an atom, is that exo or is it endo? Anyone, any idea?
Exo.
I said, so the first one is exo. For example, so the first, or we can say that the electron affinity of the atom is always exo. And the electron affinity of ions is always endo. And there's a reason for that. The reason is that oxygen is a very electronegative atom. Like if you have an oxygen atom, the oxygen atom, let's say you've got this oxygen atom, right? So the oxygen atom is very electronegative. So it will, if it sees an electron, its nucleus will do all the work. It will pull that electron towards itself. It's going to steal electrons from some other atom and it's going to gain electrons, right? So it's going to do all the work itself. No energy is required from the outside. So all the work will be done by the atom. It's going to be an exothermic process. So, but once an oxygen atom gains an electron, it now becomes a -1 ion. So once the atom has already gained the electron, it's now in the form of an ion. Now it becomes very difficult for it to gain electrons because there's mutual repulsion that's happening. The electron is getting repelled and this atom, I mean, they're both mutually repelled. So it becomes really hard to gain electrons. So the next one is going to be endothermic. All the electron affinities of the ions are going to be endothermic. First one is easy. That's exo. The second one is difficult. That's going to be endothermic. It becomes more and more difficult to gain electrons once you become a negative ion. Okay. Umar, is this clear? See, Anna, Risha, is this clear?
Yes.
Okay, so just remember the first one is for the atom is exo. It pulls the electron itself. But after that, there's mutual repulsion. So let's move on to the Born-Haber cycle now, which is what is the Born-Haber cycle? So let's quickly jump to this. So we're done with atomization, we're done with lattice energy, we're done with this thing, electron affinity. So now we're going to move towards the Born-Haber cycle, which is basically a Hess cycle that is associated with ionic compounds only. So this one is specifically for ionic compounds. So what happens in the Born-Haber cycle is that all Born-Haber cycle for all ionic compounds is going to be very, very similar. And there are multiple ways of drawing this. Remember, it's a cycle, so you can sort of make it upside down as long as the parts are connected the same way. I mean, for example, if I want to make, you can pick any starting point and you can make the whole cycle. So it's always going to be made the same way. So let's say we draw a Born-Haber cycle, and the Born-Haber cycle, the purpose of a Born-Haber cycle specifically in most cases is to measure the lattice energy. Okay, so you're trying to measure the lattice energy or the energy that is released when gaseous ions they turn into solid ionic lattice. So let's say we start off with MgCl2. So the first thing is you start off with enthalpy of formation that would be given to you. I got an Mg plus Cl2 and it's forming MgCl2. So it's Mg solid and Cl2 that's gas. And I've got another MgCl2 which is a solid, right? So I've got this thing, and that's enthalpy of formation, delta HF. So the questions are going to be very typical. Most questions are very typical. So you'll be given this enthalpy of formation. 1 mole of ionic solid is formed from its constituent elements, and the elements are in their standard state. So I usually start from this point. Now the cycle is you're going to try and figure out this other path. We don't know what that path is, but we're going to try and make one path. And if you're able to make this path, then we'll be able to apply Hess law to this. So stepwise, if I've got Mg metal and I've got Cl2 as a gaseous element, what are the steps involved to form this ionic lattice? The first thing is enthalpy change of atomization. What I need to do is I've got metallic Mg over here. What I'm going to do is I'm going to break all the bonds of Mg, and I'm going to turn it into Mg gas. And the same thing I'm going to do with Cl2 as well. I'm going to break the bonds of Cl, and I'm going to turn it into 2Cl gaseous atoms. So this step is my enthalpy change of atomization. So it's the enthalpy change of atomization of Mg, plus it's the enthalpy change of atomization of chlorine as well, because I'm turning chlorine into atoms as well, but it's twice the enthalpy of atomization of Cl, because I'm producing 2 Cl atoms. If you remember, enthalpy of atomization was that 1 mole of gaseous atoms is formed from its element, and so this is enthalpy of atomization of Mg. This is 2 times the enthalpy of atomization of Cl. First step, is this clear? This first step.
Yes.
Okay. And just don't get confused. I'm just trying to make a cycle. It's going to be a very typical cycle, which is going to be made every time. So I want to make MgCl2 the ionic lattice, right? This is what MgCl2 looks like. It's got Mg ions and it's got Cl ions. They're all attracted to each other and forming a solid ionic lattice. It's going to be a 3-dimensional lattice. So this is what MgCl2 looks like. So what do you think is the next step? Once I have atoms, right? Once the metallic Mg, all the atoms are free to move around. The Cl, they're no longer bonded to each other. They're free Cl atoms. What is the next step? I would have to turn them into ions. That's the next step, right? So the next step is Mg has to turn into Mg2 plus, and Cl has to turn into. So Cl has to turn into Cl minus 1. So how do we do that? It's Mg has got to lose 2 electrons, so it's going to become Mg2 plus gas. And Cl is going to gain those 2 electrons, that's Cl minus 1, that's going to turn into gas as well. And there are 2 Cl minus 1s, right? So what do you call this thing when Mg turns into Mg2 plus? What is that? What term is, what energy is this? Abhi, any idea? Mg turning into Mg2 plus, what do you call that?
And that's the second ionization energy.
Okay, that's not just the second, it's the first plus the second.
Yes, exactly. For both the electrons.
It's the first plus second ionization energy of Mg. Because you're not removing 1 electron, you're moving 2 electrons, right? And what do you call this thing when Cl gains an electron? We just did this.
Electron affinity?
Okay,
Electron affinity?
that's electron affinity, right? So this one, so it's the electron affinity of Cl atoms, but 2 of them. So it's double the electron affinity of Cl atoms because you're doing it for 2 Cl atoms, right? Electron affinity is defined for 1 Cl atom. So this step, this is the ionization step. And then you've got the final step, which is that gaseous ions, they turn into ionic lattice. And that's your lattice energy. By definition, that's your lattice energy, that 1 mole of ionic lattice solid is formed from its gaseous ions. So this is a typical Born-Haber cycle. Okay, and you can make this for any ionic compound. You have enthalpy of formation, elements in this standard state turning into an ionic solid. And how do you do it stepwise? You turn it into gaseous atoms first. You break the Cl-Cl bond, and then you ionize them. So they turn into gaseous ions. So that's ionization energy plus the electron affinity. And then you connect them together to form the solid ionic lattice, and that's your lattice energy. And we can do this for any ionic compound. But is this one clear? Jean Claire, Wasim, Umar, Alicia.
Yes, sir.
Yes.
Just we can make it for another one. Let's say Al2O3 is an ionic compound. So let's try and do it for Al2O3. So remember, all these energies would be given to you. The only one that would most likely not be given to you, or one of them will not be given to you. So you can apply Hess law, but we'll do the calculations later on. First, let's construct the cycle. So I'm going to do it for Al2O3 now. So aluminium, the element solid, which is metallic, and oxygen, which is O2 gas. The elements, they form Al2O3. So it forms Al2O3, which is a solid ionic lattice. And I need to balance this. So this is going to be 2 Als and I guess 3 by 2 oxygens. You get 3 by 2 oxygens. What's the next step? Make this other path, which is atomize them first. So the aluminium turns into gaseous atoms. And the oxygen will turn into gaseous atoms as well, and 3 oxygen gaseous atoms. Like 3 by 2 oxygens, if I break all the bonds, it's going to be 3 oxygen atoms. So it's the enthalpy change of atomization of Al multiplied by 2. And it's the enthalpy of atomization of oxygen, but that's multiplied by 3 because I'm making 3 oxygen atoms. Yeah, by making 3 oxygen atoms, so it's 3 times enthalpy of atomization of oxygen. Next step would be I would ionize them. So it's going to be 2 Al, 3 plus, ions formed, and 3 oxygens, they turn into -2 ions. And they're all gaseous. And so how much is this? How many ionization energies is this for Al? For Al, how many?
First, second, third, and twice.
Again, twice as well. So it's the first ionization energy plus the second plus the third ionization energy of aluminium. 1 second. Of Al. And it's being multiplied by, now you have to be very careful about these moles because when you're doing calculations, this would be very important because there's a very high chance of error. For example, if enthalpy of atomization multiplied by 2, right? Enthalpy of atomization of oxygen, that should be multiplied by 3 because you're forming 3 oxygen atoms. And you have to be very careful with the moles over here. I mean, that's the key to getting the right answer because even if you make the whole cycle correct, one minor mistake and everything is wrong there. So you have to ionize it 3 times. The first electron, second, and the third electrons, all 3 have to go. And then you have to multiply by 2 as well because there are 2 aluminiums. Similarly, how many electron affinities of oxygen? It's going to be the electron affinity. Remember, you don't write first or second for, you just write electron affinity of oxygen. And then it's the electron affinity of the oxygen -1 ion. Right? So the oxygen first turns into -1, and then that oxygen -1 turns into -2. And you multiply it by 3 because you're doing it for 3 oxygens. And the last one is your lattice energy. That's so this one, last one is your lattice energy, and this was your enthalpy of formation. So one of the values would be missing. Most likely it's going to be lattice energy, and but you have to make the correct cycle in this case. And then so a lot of times what will also happen is that they'll give you energy values, and the cycle, I'll show you some questions now. Okay. But is this clear? Are these 2 cycles clear?
Yes, sir.
Or is going to make sure you I mean, we'll do a question, but draw these Hess cycles for me. Like Hess cycle for these ionic compounds. I've got potassium oxide. Remember, you have to be very careful about the moles. So make one for potassium oxide. That's question number 1. That's your homework. Do it. Send it in by tomorrow. Do it for NaCl. And third one is, so we'll start with questions. Take it a second. Do it for MgO. And ionic compound, just a second. Let's do it for Mg3. I'll post this in the group as well. Just the cycle. Just the cycle as it is. I said we're gonna start with some questions. They'll just have values. The only thing is they'll have values with them. The rest would be kind of exactly the same. So where's okay. Sorry, this is so we can start with that's sorry, that is actually just a second. This is the first one. They've given us value. That's for potassium oxide, right? So can you see the screen?
Yes.
So if you can see the screen, I said let's start with this one. Tell me if you can't see the screen. I said, so let's start with this one. They're asking me to calculate the lattice energy of potassium oxide. So I'm going to make the whole Born-Haber cycle, which is that I'm going to start with enthalpy of formation element. So potassium is a solid metal. That's the element. The other one is going to be oxygen. That's the element, and it's a gas. And together they're going to form what? Potassium oxide, K2O, right? Which is the solid ionic lattice, right? So I've got this thing. Alisha, can you see the screen?
Yes, sir.
And I'm going to balance this. This is going to be half oxygen, right? This one is going to be half oxygen, and so that's enthalpy of formation. They gave me the value for that as well. That's minus 361. So I know one part. That's minus 361. So what's the next part? The first thing I'm going to atomize things, right? So I'll turn them into atoms, and so it's going to be potassium gaseous atoms, and there's going to be two of them actually. So potassium gaseous atoms, 2 times, and there's going to be 1 oxygen gaseous atoms. That's 1 time. So that means enthalpy of atomization of potassium into 2. So I've been given the enthalpy of atomization of potassium, but that's going to be 89, and it's going to be multiplied by 2. Be very careful with these moles, right? Because I'm atomizing 2 of them. And for oxygen, they didn't give me anything actually. So we'll ignore that for now, but we'll bring that in later on. So what can I use for oxygen? Like, they didn't give me anything. And remember, at this point, I mean, this is an old question, so the data booklet is still with you in this older question.
After bond energy.
Kya hoga?
The
It's
bond
the-
energy.
Bond energy, right? Because turning an oxygen molecule into a gaseous atom, you're just breaking the oxygen-oxygen bond, and that is given in the data booklet. Okay, so remember, when you're doing the older questions, the data booklet is with you. In the newer questions, the data booklet would be printed next to the question. So this is equal to the bond energy. So it's going to be what's the bond energy of oxygen? I mean, you can open the data booklet breaking the oxygen double bond, that's 496. But you're you're just breaking half moles of oxygen bond. So that's 496 divided by 2. Here, that is what you got from the data booklet. And somebody should have a data booklet with them. I'll be asking for values. Next step, I'm going to ionize this. So if I want to ionize this, 2 potassium ions, gaseous, plus oxygen is going to turn into -2 gaseous. Now they've given me the electron affinity of oxygen. That's like gaining the first electron and then gaining the second electron. That's -141. So that's -141 and plus 798. Because that is the energy that is needed to turn oxygen to oxygen -2, right? What about potassium turning into potassium +1? For that, again, the data booklet has those values. Can somebody look up the data booklet and tell me what the values are for potassium turning into potassium +1?
$418.
Get there 4?
418.
418, right? 418, and that's going to be multiplied by 2 and plus 418. That's going to be multiplied by 2 because I've got 2 potassiums over here. So again, I'm just going to repeat. Enthalpy of formation that was given -361. I had to atomize it. Potassium turning into gas and oxygen turning into gas. Potassium was already given atomization. For oxygen, it wasn't given, but that's equivalent to the bond energy because I'm just breaking the oxygen-oxygen bond over here to turn it into an oxygen atom. Potassium turning into ions, that's given in the data booklet, that's 418 times 2 because you got 2 potassiums, and oxygen getting 2 electrons, that's also given over here. Only thing missing now is the lattice energy. That's not given. So that is what you're going to look for. So you can get what is the Hess law? That's one path is equal to the other path. So that means -361 is equal to what? It's equal to 89 times. Now you have to be very careful with the calculations. So it's 89 times 2 plus 496 divided by 2. What else? Plus 418 times 2 plus 798, sorry. And then it's -141. And then it's plus lattice energy. So it's plus lattice energy, and you have to make lattice energy the subject of the equation. So I guess you can just flip these sides. Try and solve this, okay? But be very careful with the calculation. You have to figure out lattice energy.
Sir?
Yes.
Sir, why are we like dividing 496 by 2? Shouldn't we multiply because it's going from half to full?
Hey, bond energy. Bond energy is yeah, I did explain this as well. As a matter of bond energy. First thing, I told you that I think somewhere over here. Just a second. As somewhere at this point, when we were doing atomization, right over here. First thing, I told you that first thing, bond energy is only defined for gaseous molecules, TK or atoms. Now, how many? If I have an O2 bond, like if I have 1 mole of O2, how many bonds do I have? That's 1 mole, right? You clear as that's 1 mole of O2 bonds, right?
Yes.
So because if I have, so it's 1 mole of O2 bonds. So if I break the bonds over here, I'm breaking 1 mole of bonds, right? So if I have 1 mole of this, right? So I'm breaking 1 mole of bonds. So so to break 1 mole of bonds, that requires 496. Yeah, but how many bonds am I breaking? That's half moles, right? Is that clear?
Yes, sir.
So which is why that's going to be 496 divided by 2. So remember this, that If there's a half in front of it, that means you're breaking half moles of bonds, not 1 mole. ठीक है, इसको ही देखना. When you're looking at bond energies, look at this thing. Look at the number over here, not on this thing. Because if I break 1 mole of bonds, I'm going to get how many oxygen atoms? I'm going to get 2 oxygen atoms, right? So don't look at the number over here. When you're dealing with bond energy, look at how many bonds you're breaking. Okay?
Right, sir.
So did anyone get the answer for this one? And remember, this is a very typical question. It comes in almost every paper, and it's exactly almost the same, except that the ionic compound is different. So what do we get for this?
Negative 3153.
It's negative 31. Has anyone else tried this? Now, the whole problem with this question is negative 3153. So the paper number is given over here. I'll just quickly check this one. I'll tell you what the problem with this question is. Like probably problem with the math. Hopefully this one is the right one, but did anyone else try this and get a different value? As this one is 9701, that's summer 1742. 1 second. Did anyone try and solve this whole thing? That one is wrong. And let me just check. Did we do anything wrong? Minus 361 is there. That's minus.
Sir,
2.
my answer is minus 2280.
Okay, minus 22. Yes, that's the correct one. Actually, now here's another problem. So remember this. Okay, the chances of error in solving this question are huge. Chances of making silly mistakes. Okay, even if you get this cycle right, get the numbers moles right, okay, you have to multiply this by 2, this by half, this by 2, okay, you have to get every small detail correct. I mean, the question is not that difficult, except that you have to be very tedious with your working, okay? And even once you have made the whole S cycle and everything is written in front of you, be very careful on your calculator. If 5 students solve this question, most of them get the answer wrong. Even when you reach this point, when everything is straightforward, when everything is written down, okay? So minus 2280 is the correct one, okay? You should try and solve this again. Make sure when you're solving this, especially when there's a lot of addition and subtraction, try and make sure that you do it, double check this thing, okay? I mean, this question has a lot of, people face a lot of problem when they're solving it using their calculator. It's, they always get a wrong answer. Even everything is perfectly fine, but still they get the wrong answer. Okay, so make sure double check, triple check your calculations when you're doing this question. Okay. But is this clear? This Bond cycle? Okay, tomorrow we'll try and do more questions on this. We'll try to do the whole worksheet actually, but all questions would kind of pretty much be the same or similar to this. And the only thing you have to be really worried about is ये 2 यहाँ पे लगाया कि नहीं लगाया, ठीक है? Is this there? Is this 2 there? Did you miss out on anything? ठीक है? Did you get the signs correct? ठीक है? When you're rearranging, when you're trying to solve this on your calculator, you have to be very careful about that, ठीक है? Otherwise, I mean, you lose out on at least 1 mark. If you do all of this, out of the 3, you'll probably lose out on 1 mark, which is the answer, the final answer, ठीक है? So tomorrow we'll try and do more questions on this, ठीक है?
Sir, can we do the latest one?
Yeah, let us see. It's gonna. I think it's 2020. This one has 2020, 21 as well. I'll send this. I will send this worksheet. Share this with you, okay? Or latest we best. I'll open the papers, okay, to solve the latest ones as well. So let's continue tomorrow.
Thank you, sir.
Okay, take care.